So I'm hoping that this page is familiar to you, because I did email it out and say, look, you know, rather than spend the first, it's bad enough, and it's not your fault, my fault, that it takes me a while to get set up in here, but I didn't want to spend a lot of the lesson going through these terms. So I'm hoping you've read what we're covering today. A probability distribution is a pompous way of just listing out all the different outcomes of an event and the associated probabilities. So the most obvious example would be, right, when you roll a dice, it can be a 1, a 2, a 3, a 4, a 5, or a 6. So I'm going to roll the dice once, and I'm going to call my score capital X. So the probability that capital X equals 1 is 1/6, 1/6, 1/6, 1/6, 1/6, and 1/6. That is a probability distribution. This list of numbers is referred to as the sample space. It is all of the different outcomes that can happen. It is a variable because its value is not known until we roll the dice. It is a random variable. Unless there is something dodgy about the dice, the outcome of rolling the dice cannot be predicted. And it is a discrete random variable because it can only take certain values. It is not a measurement. You know, I'm not hitting one of those things at the fairground where it measures how strong you hit. That's not discrete, but this is discrete. And almost exclusively we deal with these discrete random variables. So a probability distribution fully describes the probabilities of the outcome of an event, and probability distributions are presented to us in one of three ways. A table, most common. Some sort of description, which is called a probability mass function. For example, they've presented what I've just done behind myself here as they've just said it's always 1/6, whether it's 1, 2, 3, 4, 5, or 6, or a graph, And obviously, with the dice, all the probabilities are the same. So this is a special case that we call a discrete uniform distribution. So I need you to be sort of familiar with those, particularly those terms that are in bold on that sheet, and hopefully you had a look at it already. And if you haven't done so, I emailed it out, I encourage you to make some notes on that. I'm going to start by using these tables. Okay, the notation's a bit funny, isn't it? You know, little x, big X. Don't know, that's spooky. So let's think of a second example. You flip a coin twice. X is the number of heads that you get when you flip a coin twice. All right. So you might not get any heads. You might get one head, and you might get two heads. So using your little tree diagram. So for those at home, while I was setting up, I asked people to do a quick tree diagram for flipping two coins. What's the probability of each of those outcomes? Okay, what's the probability of no heads, one head, or two heads? Hopefully you can fill that in from your little tree diagram that you've already drawn. I'm going to quickly knock it up anyway. So this time we don't get a uniform distribution because there's a couple of ways I can get a single head first, then tail first, then head. So this probability distribution is the first one we've met that's not uniform. Okay, maybe without drawing any more, or maybe with drawing more, can you now redo that for flipping a coin 3 times? If I flip a coin 3 times, what's the probability distribution going to look like now? The probability of no heads, one head, two heads, or three heads. What's that probability distribution going to look like now. Obviously, we've got up to the 2-head stage. Maybe we can get further. So I've just made a note on my tree diagram of how many heads each of the 8 outcomes involves. They're all going to have a probability of 1/8, aren't they? So no heads, that's just one way. 1 head, well, there's 3 ways that can happen. Head, tail, head, tail, head, tail, 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 head. 3 ways. They've all got a probability of 1/8, so that's 3/8. 2 heads. Now I just note at this point that those 2 non-uniform distributions that we've looked at are symmetrical. They're symmetrical. There's a sort of, there's a thisness to them, maybe if they could be drawn with bars, but there's a shape. Now, not all probability distributions are like that, but some are. And some are not symmetrical, but still have that idea of starting with low probabilities and having higher probabilities in the middle. And I'm not going to say any more about that until tomorrow, but yeah, I make that point now. So, this allows me to illustrate one key fact about probability distributions, which is nothing new, and that's the probabilities all add up to 1. Okay, so I don't think that's mentioned there, but it's hopefully fairly obvious. Yeah, so the probabilities in any probability distribution add up to 1. And so that leads us into the sort of problem that you tend to get with these sorts of questions. And I'm hoping at this point that you people have seen my email about having access to a book. I'd like us to have a go at a couple of questions from this exercise. It'd be really nice if you managed to download or you had access to the online book, just so I'm not always printing for you. It was useful to print last week because we were actually using tables, and that was helpful. But so if that means having your phone out, that's absolutely fine. Other than that, I'll try and get it on the screen, but it just means we can work at different paces. So can I ask you to have a look, and we're on, if you are going to use your electronic version, we're on page 87. So forgive me, slightly funny order, but I'd like to have a go at question 10 first. So the probabilities here are, I'll write them here, 1/8, 1/4, 1/2, and 1/8. And then I'd like to have a go at question 8. So 10 and 8 are questions which are based around this idea of a probability distribution presented to us in a table. Okay. So with this question here, this is just 5/8 because it's the probability of 2 and 3 added together, not the probability of 1. So it's a half, which is 4/8 plus 1/8, so that's 5/8. Probability of less than 2, so that's just 3/8 because that's the probability of 0 and the probability of 1 added together. And the probability of greater than 3, 0. You can't get, in this particular case, whatever x is, you can't get a score of greater than 3. So those are our 3 up. Why did we do it as a decimal? Leave it as fractions, for goodness sake. And then these sorts of questions, this is just algebra, isn't it? This is just algebra. So, you know, I know that if I add those 3 probabilities together, I've got a half plus a quarter, sorry, half plus a quarter, which is 3/4. I've got minus 1a plus 1a plus another a, so that's, and I know they've got to add up to 1. So a is a quarter. A is a quarter. And you could then go on and say, right, if a is a quarter, that means that's 0, that's 1/4, and that's 3/4, which is a good way of checking that it's right, because those probabilities do indeed add up to 1. Okay, so probabilities presented to us in tables like this, all good stuff. The other way, well, there are 2 ways, the graph, but very often these probabilities are presented to us in a table that looks like this. Is that going to be any bigger if I look at it? Yeah, right. So we'll have a look at question 6 and question 7. So this is another one of the probability mass functions that are referred to earlier, although this is more complicated than the uniform distribution that we were presented with before. I say it's more complicated, it looks scarier than it is. Okay? Now, I would always approach a question like this, unless it was one with lots of different values, I'd always approach a problem like this by putting it into a table. So if I look here, I can see that this variable x can be 1, 2, 3 or 4. If it is 1 or 3, its probability is some constant k times x. So for example, if when x is 1, that will be k times 1, so that's k. And when it's 3, that will be k times 3, which is 3k. Do you want to see if you can answer the rest of that question? The probabilities for 2 and 4 are slightly different, but they want you to find the value of k, and therefore the probability x is greater than 1. Question 7 is a similar question. So when x is 2, we've got 2 minus 1, which is 1, so that'll be 1k. And when x is 4, 4 minus 1 is 3, 3k. So we get 8k is 1. 8k is 1. So k is 1/8. Yep. And I have, so I'm going to fill in the probabilities. So the probability x is greater than 1, 7/8. 7/8. Okay. So have a quick go at number 7, and then when you've completed that, sorry, there's some more of those on. Right, they must be in the mixed. Oh no, we've got 7. Well, I'll tell you what, do 7 and then do the remaining questions that you haven't done. Yeah, starting at question 4. So do 7 first and then go back to the top of the page and work through the rest of the questions in that exercise. Now,